Every phone, tablet, and smart device you own constantly screaming into the air, begging to talk to something else. Invisible radio waves carry your Netflix stream, your texts, and your credit card number at the speed of light. Today, I'm breaking down every major way your devices communicate, from the brutal truth about Wi-Fi to the invisible mesh network your smart bulbs are quietly building. Starting with the one everyone blames when the internet is slow, Wi-Fi. Wi-Fi operates in unlicensed 2.4 and 5 gigahertz bands that it shares with microwave ovens and Bluetooth, which is why your connection turns to garbage the second someone heats up leftovers. When a router advertises 1200 megabits per second, that assumes perfect conditions. In a real apartment, you're looking at 100 to 300 megabits after walls eat the signal and neighbors flood the same channels. Here's where it gets brutal. One weak device needing constant retransmissions can drag down the entire network because Wi-Fi is a shared medium and everyone waits their turn. Your ancient smart fridge can actively slow down your gaming PC, which makes zero sense until you realize they're both screaming into the same invisible channel. Modern Wi-Fi 6 fixes this by slicing channels into subcarriers to serve multiple devices simultaneously, turning a single lane road into a highway with dedicated lanes. But if you think shared spectrum chaos is complicated, wait until you hear about the protocol that hops frequencies 1600 times per second just to avoid getting jammed. Bluetooth. Bluetooth was named after a 10th century Danish king named Harald Bluetooth Gormson, because apparently the best way to honor a guy who united Scandinavian tribes is to make him the mascot for uniting communication protocols. But here's where it gets weird. Your wireless headphones are performing mathematical acrobatics you never asked for. Bluetooth chops the 2.4 gigahertz band into 79 separate channels and hops between them up to 1600 times per second. Your earbuds are literally playing frequency hopscotch every 0.625 milliseconds just to avoid interference from your microwave. Then there is audio latency. When you stream music, that audio gets encoded, chopped into packets, blasted across the air with error correction, and buffered on the receiving end to smooth out jitter. The entire journey adds 100 to 300 milliseconds of hidden delay. That is why lip sync feels completely off when you watch video with Bluetooth headphones, but music sounds perfectly fine. You never notice the lag when there is no visual reference. And here's the kicker. Everyone thinks buying a device with Bluetooth 5 means better audio quality automatically. Turns out, no. Audio quality depends entirely on which codec your devices support, not the version number printed on the box. But if you think regular Bluetooth is doing a lot of invisible work, wait until you see what its low-power cousin is pulling off while literally asleep. Bluetooth low energy. Bluetooth low energy creates the illusion that your fitness tracker is always connected and monitoring your heart rate in real time. But here's the thing. That tracker is actually asleep 99% of the time. The radio only wakes up for a few milliseconds per second to fire off a packet, then immediately crashes back into deep sleep mode where it sips microamperes of current. To you, the data looks smooth and continuous on your phone. But at the electrical level, the device is practically comatose, working just long enough to whisper a number and then going dark again. This trick is what makes battery lifetimes of months or even years possible on coin cells that hold maybe 200 milliamp hours, which is nothing. BLE was introduced in Bluetooth 4.0 around 2010 specifically to solve the problem of sensors that need to run forever but don't need to blast data constantly. A heart rate strap might sample once per second and send a tiny packet every second or two, spending perhaps 3 milliseconds transmitting and the remaining 997 milliseconds doing absolutely nothing. Active less than 1% of the time, yet appearing continuously connected. That design philosophy has real consequences. Some BLE trackers are sold with non-replaceable batteries because the expectation is they'll last the entire useful life of the product without recharging. Protocol design directly determines whether a device needs a charging cable every night or runs for 2 years untouched. But if you think a heart rate strap is an extreme case of low power engineering, wait until you see what happens when your phone starts talking to cell towers that cover entire cities. Cellular networks. Like, Charsa, your phone doesn't just connect to a single tower and sit there. It's constantly negotiating with multiple cells simultaneously, and it has been since you started reading this sentence. Cellular networks evolved from analog voice calls in the early 1980s 1980s with first-generation systems through digital 2G around 1991 that introduced SMS, to 3G from 2001 pushing megabit speeds, 4G LTE around 2009 delivering hundreds of megabits per second, and 5G from 2019 onward with multi-gigabit theoretical peaks. But here's where it gets weird. The infrastructure supporting this isn't uniform at all. Cell sizes range from macro cells covering kilometers down to femto cells that cover tens of meters indoors, basically the size of a single room. Your phone maintains simultaneous connections to multiple cells and frequency bands, which is a fancy way of saying it's talking to several towers at once and combining the data streams. The invisible orchestration happens when you're moving. Drive down the highway at 100 kilometers per hour while streaming music, and your phone switches between dozens of cells during that trip. Each handover happens in tens of milliseconds without you noticing a thing. The network is making real-time decisions about which tower gets your traffic based on signal strength, load balancing, and available frequency band. It's one of the most complex control systems deployed at planetary scale, and the fact that it works at all, let alone reliably enough that you can video call someone while barreling down the interstate, is borderline absurd. But if you think invisible radio orchestration is impressive, wait until you see what a simple wire can do. Ethernet. Almost every single wireless device in your home has an invisible Achilles heel, and that Achilles heel is the air itself. It's shared, it's noisy, and it's fundamentally unstable. Ethernet doesn't care about any of that because it doesn't use air at all. Ethernet has been reliably moving data since 1973 when researchers at Xerox PARC built the first version running at 2.94 megabits per second. The modern version was standardized in 1983 at 10 megabits per second, and from there it just kept scaling. Fast Ethernet hit 100 megabits in 1985, Gigabit Ethernet arrived in 1998, and today you can get 10, 40, even 100 gigabit connections if you're willing to pay for the gear. A typical home gigabit link delivers sustained hundreds of megabits per second with millisecond latency and packet loss so low, it's basically a rounding error, completely immune to RF interference, neighbor congestion, or someone turning on a microwave. But here's where it gets weird. Power over Ethernet means you can push both data and electrical power down the same cable. The original standard provides 15.4 watts, enough for IP phones and small access points. The newest spec goes up to 90 watts, enough to run a full-featured security camera with heaters and pan-tilt motors, all over a single cable with no separate power brick. This is why competitive gamers insist on cable. The difference between 5 milliseconds of jitter and 50 milliseconds is the difference between hitting the shot and watching the kill cam, and wireless cannot promise you that consistency no matter how many bars you see. At least Ethernet doesn't randomly drop packets when someone closes a door, unlike the next protocol on the list. Universal Serial Bus. Yes, USB has gone from a tangled mess of legacy ports to the connector that does everything. And I mean everything. The problem is, that flexibility became a nightmare. The evolution is straightforward. USB 1.0 launched in 1996 at 12 megabits per second, barely faster than downloading a single MP3. USB 2.0 hit 480 megabits in 2000. USB 3.0 reached 5 gigabits in 2008. USB 4 landed at 40 gigabits in 2019, faster than most home internet. Then USB-C arrived. Reversible, elegant, finally solving the flip it 3 times problem, and it can carry basically anything. DisplayPort for monitors, Thunderbolt for Pro Gear, power delivery pushing up to 240 watts at 48 volts. Here's where it gets weird. That identical oval hole on your laptop can represent completely different realities. One USB-C port drives an 8K monitor, charges at 100 watts, and transfers at 40 gigabits. The port right next to it. USB 2.0 speeds from 2000 and barely enough power to charge a phone. Both look identical. Same thing with cables. One supports 40 gigabit Thunderbolt with full power delivery. Another with the same connector is wired for USB 2.0 and basic charge. Zero visual difference. The engineering flexibility that unified everything created a situation where you need a flowchart to figure out which port does what. But if you think decoding USB ports is confusing, wait until you hear about the communication protocol that only works when you're basically touching the device. NFC lets you buy coffee by tapping your phone on a reader, and somehow that's more secure than swiping an actual piece of plastic. Here's the thing, near-field communication runs at 13.56 megahertz based on ISO standards, with the NFC Forum founded back in 2004 by Sony, Philips, and Nokia. It works at exactly 2 to 4 centimeters, limited by magnetic field coupling between coils, and that absurdly short range isn't a flaw. That's the entire point. It guarantees you are physically intended to pay, unlike some wireless tech that could trigger from across the room, which is, not ideal for your bank account. When you use Apple Pay or Google Pay, your real card number never actually travels anywhere. Instead, NFC card emulation sends a tokenized dummy number with a dynamic security code generated fresh for that single transaction. Someone intercepting the radio signal gets nothing useful. Zero. The whole cryptographic exchange spanning encryption, tokenization, and risk analysis compresses into roughly 1 second. Data rates crawl between 106 and 424 kilobits per second. Fast enough for payment tokens, completely useless for sending photos. But that limited bandwidth is exactly what makes the secure magic happen. And if you think that's clever, wait until you see how your smart home devices quietly relay messages through your light bulb. Zigbee builds on the IEEE 802.15.4 standard from 2003, operating at 2.4 gigahertz with 16 channels and a raw data rate of 250 kilobits per second. But here's where it gets weird. Zigbee uses mesh networking, meaning your smart home devices form an ad hoc relay. Mains-powered bulbs and plugs act as repeaters, quietly passing along messages for battery-powered sensors that sleep for months at a time and wake on events. With 16-bit addressing, a single Zigbee network can theoretically support up to 65,000 nodes, which means adding more Zigbee devices actually improves network reliability and range, the exact opposite of Wi-Fi congestion, a rare case where more stuff makes things better. Your motion sensor in the basement can talk to your hub 3 floors up by bouncing through a hallway bulb, a bedroom outlet, and a kitchen dimmer switch. Each hop extends the reach without you doing anything. It's self-organizing, self-healing infrastructure that most people don't even realize exists in their walls. But this also means unplugging a single smart bulb can cut the route for a distant door sensor. Your lamp was a critical infrastructure node and you just killed it. The network will eventually heal itself and find a new path, but you've got minutes where that sensor is suddenly invisible. Pull the wrong bulb, and 3 devices downstream go offline until the mesh recalculates. Nobody warns you about this when you're setting up your first Zigbee network, and most people only learn it when they start troubleshooting phantom disconnect. If you think that 2.4 gigahertz shared band is chaotic though, wait until you see how Z-Wave completely dodges it. Z-Wave deserves more credit than it gets. While everyone's busy arguing about Wi-Fi channels and Zigbee mesh drama, this protocol has been quietly connecting smart homes since 1999 by doing something genuinely clever, avoiding the 2.4 gigahertz disaster zone entirely. Developed by a Danish company called Zensys, Z-Wave operates in sub-gigahertz bands around 868 megahertz in Europe and 908 to 916 megahertz in North America. That might sound like a minor frequency difference, it's not. Those lower frequencies have longer wavelengths than 2.4 gigahertz signals, which means they're better at diffracting around obstacles and punching through walls. Your basement water sensor that would drop off a 2.4 gigahertz network every other day because there's a concrete floor and a furnace in the way, Z-Wave doesn't care. The signal just wraps around that stuff. Same goes for garage door controllers, in-wall switches behind metal junction boxes, and any sensor buried in a corner of your house where Wi-Fi goes to die. Z-Wave's data rates evolved from 9.6 kilobits per second to 100 kilobits per second with Z-Wave Plus. Nobody's streaming video over this, but for control messages telling a lock to unlock or a switch to flip, it's more than enough. Then in 2020, Z-Wave Long Range showed up claiming line of sight distances up to 1 mile. That's not a typo. If you've got a detached garage or gate at the end of a long driveway, Z-Wave Long Range can actually reach it. The whole ecosystem is tightly controlled by Silicon Labs and the Z-Wave Alliance, which means devices have to pass certification before they can carry the logo. That's why Z-Wave has a reputation for it just works interoperability. You're not gambling on whether a random motion sensor will talk to your hub, but if you think a few hundred megahertz of frequency difference is subtle, wait until you see how invisible infrared communication manages to control half the electronics in your house. Infrared. Infrared communication is one of those technologies nobody thinks of as wireless, but it's been beaming invisible digital commands across living rooms since the 1980s. When you point at a TV remote and press a button, an infrared LED fires off bursts of light at wavelengths around 850 to 950 nanometers, modulated at carrier frequencies like 38 kilohertz. Protocols like NEC encode 32-bit commands with precise microsecond timing. To you, it feels instant. To the device, it's a structured packet of light pulses, complete with checksums and addressing, flying through the air at the speed of light. Here's where it gets interesting. Infrared light does not penetrate opaque objects. You need line of sight or at least a wall reflection to make it work. This is why pointing is literally the addressing mechanism. Your arm and the remote's direction determine which device responds. Two TVs in adjacent rooms won't both respond unless the doors are open. The gesture itself is part of the protocol, which is kind of elegant, but infrared remotes are unidirectional. The remote sends codes, the device responds, and there is zero acknowledgement back. You press the button, you see the TV change channels, and that's your confirmation. Behind the scenes, the receiver is filtering out ambient light noise with bandpass filters tuned to that 38 kilohertz carrier, picking out the modulated signal from the chaos. At least infrared keeps things simple with its line of sight limitations, unlike the next protocol, which is designed to route messages through walls, furniture, and entire buildings without you ever notice. Thread. In 2014, Google, ARM, Samsung, and a few other companies decided to do something almost no one does in consumer tech. Build a smart home standard that runs on actual internet address. That standard is Thread, and it is quietly laying the foundation for your light switch to be a first-class citizen of the internet instead of some proprietary island that needs a bridge box to talk to the outside world. Thread is built on the same IEEE 802.115.4 radio layer as Zigbee, operating at 2.4 gigahertz with a raw data rate of 250 kilobits per second. But here's where it gets different. Thread is an IP-based mesh network using IPv6. Each Thread device gets its own IPv6 address on tens of kilobytes of RAM, which sounds impossible until you realize they're using something called 6LoWPAN header compression to squeeze those massive IPv6 headers down to a manageable size. The result is that your door sensor is not just a dumb endpoint behind a hub. It is an addressable internet node that speaks the same language as web servers and cloud services, all while running on a coin cell. Thread networks are self-healing and leaderless, meaning there is no single coordinator whose failure brings the whole thing down. Instead, routers in the mesh elect a leader among themselves, and if that leader fails, another node takes over without you doing anything. Multiple border routers can connect the Thread mesh to the broader IP network, so if one goes offline, traffic just flows through another. This IP native design is a subtle but profound shift. In a Zigbee or Z-Wave world, your devices live on a proprietary island, and a bridge translates their command. With Thread, the devices themselves are IP endpoints from the start, which means simpler setups and more predictable behavior across brands, even if you never realize that your light switch is hopping IPv6 packets around a self-organizing mesh. But if you think having every gadget on its own IPv6 address is the peak of smart home evolution, wait until you hear about the application layer that runs on top of Thread and promises to finally make different brands talk to each other without proprietary nonsense matter. So we've gone through every major way devices talk to each other, from ancient infrared remotes to mesh networks quietly self-healing in your walls. But here's the thing, for decades, none of that actually worked together. Your Zigbee bulb couldn't talk to your Z-Wave lock, your Alexa couldn't control your Google devices without weird workarounds, and every brand demanded its own app and cloud account. Matter is the first real attempt to fix that mess. Announced as Project Chip in 2019 and released as Matter 1.0 in October 2022, it's backed by basically everyone: Apple, Google, Amazon, Samsung, the entire smart home industry finally agreeing on something. And here's where it gets interesting. Matter isn't a radio technology. It's an application layer protocol that runs on top of existing network. High bandwidth devices use Wi-Fi, low power sensors use Thread for mesh routing, Bluetooth low energy handles initial setup. The real genius is that Matter standardizes what devices are and how they behave, not just how they connect. Every compliant smart light implements the same attributes and commands. Every smart lock, same thing. Your phone, your voice assistant, your TV, they can all control the same devices locally without duplicating configuration or needing vendor cloud. Multi-admin functionality means you can add a single bulb to both Apple HomeKit and Google Home simultaneously, and they both just work. For years, platforms like Alexa had to write hundreds of proprietary integrations for individual brands. Matter flips that around. Controllers only need to understand the Matter specification to work with any brand's device. You buy a bulb from brand A, a lock from brand B, control them all from whatever platform you already use, no bridge boxes, no separate apps. Whether it actually delivers depends entirely on whether vendors stick to the spec instead of bolting proprietary extensions on top. But for the first time in smart home history, the incentives are aligned. Everyone wants this to work. If you enjoyed this video and want to see more, click the video on the screen now.